Okay, let's talk about one type of surface area problem. So we're going to find the surface area of the part of the sphere inside the cylinder x squared plus y squared equals a times y. I'm sorry, not a, 1 times y. Okay, so there's a little bit to unpack here, and I think following these steps will help simplify the process. First, you need to find the limits of, or the ranges of your coordinates. You also need to know what coordinates to use, but it should be kind of obvious that some sort of cylindrical or polar thing will be useful. And then second, you'll want to find the dA associated with this. And finally, you want to do the integral, and that's the easiest part. It's just mechanical. But this is somewhat hard to see at first glance. So what is actually going on here? You can tell this is kind of a shifted circle. So let's do the usual complete the square thing. So if we do y squared minus y, you have to stick a 2 there to make any sense of this. So it's 2y times a half, and then that's the thing we'll complete. So it'll be y squared minus 2y times a half plus a half squared minus a half squared. So this will finally be y minus a half squared minus a fourth. So therefore, this funny looking equation, you can rewrite it as x squared plus y minus a half squared equals a half squared. So in other words, it's just a circle, and it's shifted up a half and has radius a half. Just let's pretend that I just drew a circle. So this kind of suggests that I think polar coordinates is a nice way to do this. So if we use polar, then of course x equals r cosine, y equals r sine. So if we plug this in, then I'm going to plug it into the easiest looking equation. So I'll do this one. So then we get r squared equals r sine theta. So r equals sine theta. That is the polar representation of this curve. Okay, so now let's just get the theta limits, because we know that the range of the r, it'll just go from 0 to sine theta when we integrate. So the theta, it'll start at 0, and we'll stop at theta equals pi. So theta goes from 0 to pi, and everything inside that cylinder, that'll just be r ranging from 0 to sine theta. Okay, so now that we have the limits, we can now start to talk about what we're integrating. And that's the subject of what is dA. So dA, you have to do not be confused. We're not doing the dA of this one. We're not doing the dA of the inside. Remember, this equation corresponds to the inside. This is what we want the surface area of the sphere. So it'll be for the x squared plus y squared plus z squared equals 1. We'll use the same coordinates as before. That is cylindrical. So x equals r cosine theta, y equals r sine theta, and z will be free. So when we plug this in, we'll get r squared plus z squared equals 1. This isn't as good as spherical, but remember, we want the same coordinates as before. And spherical would have been much worse, I think, if we tried it here. So, we solve for z, and it should be plus or minus the square root of 1 minus r squared. I'm just going to choose the plus and multiply a times 2 at the end. Right? Because, I mean, if you kind of draw what's going on here, we have a sphere, and then there's just this funny cylinder. I'm just going to choose the top half. Right? I think that's I think it's a little easier than having to mess around with this plus or minus. So now that we have z as a function of r, now we have our parameterization. So what are the free variables? The free variables are z and I'm sorry, not z. Yeah, maybe I shouldn't have said free. Z will be z, and we need to solve for z. Really, I think the free variables will be theta, because if you look at the graph here, theta. Yeah, everything inside the cylinder, our theta is varying and our r is varying, so these will be the variables we'll use. So r will be a function of little r and theta, and we'll be using r cosine theta for the x part. You'll have r sine theta for the y part, and for our z, we'll use this square root. So this is, again, the parameterization. And so now we just need to compute what exactly dA looks like for this. Okay, so let's compute the partial derivatives, because remember, dA will be that cross product thing. It'll be r cross d theta dr. we have a little cat fight going on here. Never mind. So let's compute the partial derivatives. R theta will be minus r sine theta, r cosine theta, 0. And then finally, r sub r, partial derivative in r, this will be cosine theta, sine theta, and minus r divided by that square root. So let's again use our nice trick of computing the dot product. Well, that should just be, I'm going to do the xy part first. So we'll have minus rsc plus rcs, that's obviously 0. And then for the z, that'll be 0, clearly, because the first component is 0. So the dot product is 0, so our cross product reduces to the product of the lengths. I think these cats need to study some mathematics. That'll calm them down. So the lengths of these vectors will be just r, and let me just do this one separately. So the length of this thing squared, it'll be cosine squared plus sine squared plus r squared divided by 1 minus r squared. So this is 1. So if I put a denominator, I'll have 1 minus r squared here plus r squared here. So this should just be 1 divided by this. So that means we will get 1 over that square root. So in other words, dA will be r divided by the square root dr d theta. And this may look bad, but it actually turns out to be not bad at all. So our last step is just to do the integral. And we need to remember our ranges, of course. So if we go back to what we had, our ranges were here. So theta goes from 0 to 2 pi, 0 to pi, and r goes from 0 to, looks like it was sine theta. So I'll put our theta on the outside, because there's no r there, and then I'll put my r limits here. That's the integral we need to evaluate, and I'll leave this to you. It's actually, it looks a little scary, but it's totally doable, actually. And it's a very nice, crisp answer. Thanks for watching.